So thank you very much for the introduction. So today we'll be talking about three main technologies in DeepSpeed: the training, inference, and compression. My name is Tunji. Reza will be talking about inference, and Joey will wrap up with a talk about our compression technologies. Next slide. So first I'll start talking about how DeepSpeed has reshaped the large model training landscape. Next slide. So just as a primer, let's think about data parallel training. This is the most basic way that training is done. Here you would have replicas of a model on multiple GPUs. These GPUs could be within a node or across multiple nodes. And each replica runs essentially the algorithm that's shown here on the left-hand side, where it fetches a mini batch and runs a forward propagation to compute a loss on that mini batch. It uses that loss to do a back propagation to compute gradients. And these gradients are averaged across all the GPUs. An optimizer is used to compute a specific update for the model and for the task. And this is applied to the model. And then the loop repeats where we fetch the next batch. And so basically, this is an overview of data parallel training. Next slide. So, but when we look at the large model training landscape today, here's what we observe. We see that the models are growing very rapidly in size. Transformers, which are the most frequently used dominant architecture for large language models, we see they've grown over 200 times over the last 2 years. They're growing at about 200 times every year. But the GPU hardware memory is only growing so much more slower, 2 orders of magnitude slower. And so what that means is that the data parallel training that we looked at earlier, it means that the models can no longer fit in the GPUs. So the GPU memory is basically the bottleneck to scale into larger models. Now, the reason we want to scale to larger models is because of the quality gains. We get better models when we scale to larger sizes. And so the fact that the GPU memory is not scaling as fast creates what is called the GPU memory wall, and this means that we need hundreds or thousands of GPUs to train the next generation of models, which will have trillions of parameters. And so the question is, can we afford this sort of hardware investment in order to train the next generation of GPUs? So that's sort of the first question. The next question is, even when these models get trained, think about what it takes for downstream tasks of fine-tuning or inference, which model scientists or students might want to do. It requires dozens or hundreds of GPUs, and a lot of students and model scientists don't have access to this kind of resources. So this is a problem as well. And then the final point is that there are techniques out there for addressing this GPU memory wall, such as various forms of model parallelism like tensor slicing and pipeline parallelism. But the problem is that applying these techniques requires rewriting the models. And for model sciences, this is often a painful and an error-prone experience. Next slide, please. And so before going into how DeepSpeed solves this GPU memory wall issue, let us try and understand where the memory consumption for model training goes into. If we consider mixed precision training using something like the Atom optimizer, we see that every parameter there is the FP16 parameter requires about 2 bytes to represent it. The same thing with the gradients, it's about 2 bytes as well. And then the optimizer state, the Atom optimizer state requires 16 bytes for each parameter. So in other words, each parameter in the model consumes 20 bytes of GPU memory. Next, please. Which means that a 1 billion parameter model, for example, will take up 20 gigabytes of each GPU memory if we're doing data parallel computing. And keep in mind that this memory consumption does not even take into account things like the input batch, memory for the input batch, and for the activations. Next slide. So we propose zero as a technique for overcoming this GPU memory wall. Zero is a family of composable optimizations that reduce the GPU memory cost of deep learning states, basically the parameters, the gradients, and the optimizer. And zero basically has 2 major themes, techniques that are complementary. The first is partitioning. 0 will partition the training state across the data parallel GPUs. And we have 3 stages of partitioning techniques that I'll describe later. 0 also does offloading. It offloads the deep learning states to CPU and NVMe memories, which usually have much larger capacities than GPU. So let's look through how this works. Let's consider a baseline of data parallel training where we have, n GPUs training there. And here we're showing the memory consumption for the different objects in the training state, the parameters, the gradients, and the optimizer states. So the first stage of 0, if we go down the partitioning dimension, is to partition the optimizer states. So here we see in the stage 1 of 0, we are partitioning the optimizer states. Rather than replicating it, we're partitioning it across all the data parallel GPUs. So the memory consumption for any given GPU is reduced by n. The next stage of partitioning is to partition the gradients. Similarly, this reduces the per GPU consumption for each of gradients for each GPU. And then the final stage is to partition the parameters as well. So now the model is fully partitioned in the stage 3 of the 0 memory optimization. And if we think about what the impact is for the memory consumption per GPU, so here we're looking at the bytes per parameter per GPU. Remember, we said that for the baseline, you need 2 bytes for the FP16 parameters, 2 bytes for the FP16 gradients, and 16 bytes for the optimizer state. So a total of 20 bytes is what you need in the baseline. With 0 stage 1, we're able to reduce this to less than 5 bytes per parameter. With stage 2, it drops even further to less than 3. And with stage 3, it drops to less than 1. So this is how 0 takes the step of helping us to overcome this GPU memory wall. Now let's consider the other dimension of 0's optimization, which is the offload. And so here what happens is that 0 is able to move the training states to CPU or NVMe. And we have a technology called 0 offload, where we move the optimizer states, as you can see, completely to CPU, which means the GPU GPU memory is no longer consumed with optimizer states. The next technology we have here is the 0 infinity, where we can now move the entire training states to either CPU or NVMe. We're showing NVMe here as an example, which means that for training, there's actually no GPU memory that is permanently consumed to hold the training state. Next slide, please. So I will talk a bit more about the 0 infinity technology to see how it helps to break the GPU memory wall for large-scale training. Next slide, please. So the motivation for 0 infinity is the observation that in our modern clusters, we actually have heterogeneous memory systems, right? In a single DGX2, for example, we find out that the GPU memory is actually the smallest fraction of memory in there. We have the DGX2 has a 1.5 terabytes CPU memory and about 30 terabytes of NVMe storage and just half a terabyte of GPU in all. So we want to leverage all of the memory, the heterogeneous memory that's available there. And if we're able to do this, this enables us to run a 32 trillion parameter model on 32 nodes, or run a trillion parameter model on a single node. This also helps us if you want to do fine tuning. Now we can fine tune a GPT-3 on a single node by basically leveraging the NVMe memory, the entire heterogeneous memory available on the system. Next slide, please. But there are some challenges here. The key challenges is now that we've offloaded to CPU and NVMe, we're going to be bounded by the PCIe bandwidth, which is how CPU and NVMe communicate with GPU. The PCIe bandwidth in the DGX2 is about 16 gigabytes per second, which of course is orders of magnitude slower than the 900 gigabyte per second, which is available in terms of GPU to GPU bandwidth on a single node. It's about 50x slower. So how do we overcome and prevent this becoming a performance bottleneck? The solution we use in 0 infinity is that we partition the data so that each GPU in the data parallel training will actually fetch only a partition of the data, of the model states from NVMe or from CPU. On a single node, we can get up to an aggregate of 48 gigabytes per second of NVMe bandwidth. And as you stretch that across, dozens of nodes, you are getting into the terabytes of transfer. And then once all of this is fetched into each GPU fetches a partition, they now are able to do an all gather to assemble the full state over the GPU to GPU network, which runs in hundreds of gigabytes per second bandwidth. Next slide. So now I'll show an animation of zero infinity in action. So here we see we're fetching some layers starting from NVMe. It goes into the CPU memory and then into the GPU memory, and then goes to the InfiniBand network where we're able to do an all gather so that each GPU is able to assemble the full layer. Note that each GPU here is fetching only a partition, a small portion of the layer from its NVMe. This happens both on the forward pass and the same thing on the backward pass. We have to assemble each layer. And then when the backward pass is complete, then we do an optimizer updates, which happens directly in the NVMe. So this is how Zero Infinity is able to fetch layers, fetch parameters in a very fast way without being bottlenecked by PCIe. Next slide, please. Next slide. Thank you. So we talked about how the landscape for large model training was very challenging. So let's look at how Zero Infinity has redefined this landscape. The first point is that Zero Infinity now allows you to train massive models, much larger, like 50 times larger than other techniques. We can train up to, the models in the 10 trillion to the 100 trillion parameters are now trainable. For example, the 32 trillion parameter model can be trained on 512 GPUs instead of requiring 25,000 GPUs using other techniques. This also helps to make fine-tuning of such large models or inference possible using fewer GPUs. So like a GPT-3 model, for example, can be fine-tuned on a single node of just 16 GPUs instead of using 256 GPUs. Also, Zero Infinity has excellent throughputs and scalability. In the plots on the top right-hand corner, we compare against 3D parallelism for the size that 3D parallelism can actually support, which is about 0.5 terabyte. And we see that Zero Infinity has pretty close performance there. For larger models, Zero Infinity still shows really good performance. And then the final point that we'll make here is that Zero Infinity, next click, please. We see Zero Infinity does not require any model refactoring. This just works out of the box. The DeepSpeed library will automatically do all of this for you without the model scientists having to make any change to their model code. And with that, so when we now consider how what DeepSpeed has done for the large model training, remember earlier we said that the transformer size has been growing at about 240 times every 2 years. GPU memory is just barely doubling every 2 years. With DeepSpeed and the zero line of technologies, we've actually been able to scale up the maximum model size that can be trained by 4,000 times over that 2 years. So DeepSpeed is really far ahead of even what the model scientists can design today. And so which means that we're even on current generation hardware, we're able to train much, much larger models than even the model scientists are creating today. Next slide. And just to finish up, I just want to mention some advanced model training that you might be familiar with outside of Microsoft that have been powered by DeepSpeed. The Megatron Turing 530 billion, which is the largest dense model out there, was trained using DeepSpeed. The Big Science 176 billion model, which just completed training a few weeks ago, was trained using DeepSpeed. We were involved as a team in this effort. And there are other efforts as well, like the Jurassic 1, the GPT Neo X, the Cog V2, and the Yandex, which were independent efforts that did not, were involved in, which shows how easy it is for people to actually use the zero technology to train very large models. With that, I'll hand over to, okay. So then the final things I just want to mention here, if you can just click through all of this, is that just to stepping back in terms of training, DeepSpeed has a number of technologies here. So we talked about the model scale and training speed. We also see that DeepSpeed enables democratization of AI. This is with the zero offload and the zero infinity, where individuals can train 100 billion parameter models on a single GPU. We also have support for mixture of experts, which is sort of this emerging technique that helps to reduce the computation cost of scaling to larger models. We have techniques for data efficiency, where we can train to good accuracy using fewer data samples. We have a DeepSpeed auto tuner that makes it easy for people to find, for users to find very good configurations for training the models. And finally, we're diversifying across hardware. We support both AMD and NVIDIA, and we are extending out to other GPU hardware out there. Next, please. And with that, I will hand over to Reza to talk about inference. Thank you.
Thank you, Tunji. Can everyone hear me? So here in this part, I'm going to talk about the inference technology at DeepSpeed to enable massive model inference. So first, let's talk about the inference landscape. As we know, we have different applications and different requirements at DeepSpeed inference. Next, so regarding the model size, it can range between hundreds of millions of parameters to hundreds of billions, and even the new models has up to trillion parameter models. And next, regarding the model architecture, it can be either dense or sparse for the new MOE architectures. And next, we have different hardware SKUs. It can be either single GPU, multi-GPU, single node, or multi-GPU, multi-node architecture. And regarding the batch size, the workload can be either latency sensitive with a small batch size, or throughput oriented with hundreds of requests at the same time. So with all these different requirements, one single solution cannot be efficient across the entire inference landscape. And also, most of the data scientists, they don't have access to large GPU clusters to run really large scale model inference. So our goal here in DeepSpeed inference is to provide a unified solution that can first achieve high performance for the entire landscape, and second, it can give the access to large model inference for the data scientist who has access to even very small GPU resources. Next, so to achieve our goal, we have a systematic composition of different optimizations. In the first technique, the core of the inference system is the inference optimized transformer kernels that we can achieve the best performance for different models on one GPU. And second, we have the many GPU dense optimization that we can use efficient parallelism with very minimum communication overhead to achieve high performance for even large models such as 530p model size. And also we have the sparse components optimization for the MOE models that we can get real-time performance for up to a trillion parameter sizes. And the second optimization is the zero inference that is adopted from the zero infinity in order to run very large model inference on single GPU device. So now let's look at the composition of these optimization. The first technique that we have here is the optimized transformer kernels. So here we show the different operators of a transformer layers. And as a first technique here, next, we show the deep fusion that compared to the previous approaches, we can fuse a really large number of operations together. So here we are showing, for example, the attention or the MLP or the QKV part. We are fusing 5 to 7 operations together. Next, and we also can adapt these fusion based on the batch size in order to get the best performance on different applications. Next, And we also have support for high performance int8 kernels in order to improve the efficiency on the gems up to 2x with using the int8 tensor cores. So here you're showing the 4 different gems that we can replace with these quantized gem operations. Next. And the second optimization technique is the many GPU dense optimization that we can adjust the tensor slicing parallelism within a node to use the aggregate memory and performance with low inference cost for large model inference. Next. So here as the first showcase, we show the Bloom inference. Bloom is a GPT-based transformer model that has been released as part of the Big Science project, and it has 175 billion parameters. To test this model, we use the text generation application that we insert a prompt and we generate as many number of tokens as we want. As the performance metric here on this figure, we are showing the latency and the throughput for the different byte sizes, comparing the baseline, which is a PyTorch implementation, with the DS inference. Next. So the inference technology that we use to speed up the inference first is we use tensor parallelism versus the pipeline parallelism that was used during the training. That gives us more efficient parallelism on one node. And second, we use the kernel fusion to get optimized GPU memory bandwidth and also high throughput while using large batch. So here we see between 8 to 12x improvement. And next, since we are using an efficient memory allocation on the transformer kernels, we can get up to 100x higher throughput with using DS inference. Next. So on the previous application that I was showing you is the token generation, which we already optimized. Now let's get to the prompt optimization part. So these GPT style models, they have dynamic workload, and their inference pipeline include various stages. First, there is a prompt that we process a new query, which has normally a large number of tokens. And then we get to the token generation phase, which we generate 1 token per request. Next. And also we can have different token length because of the dynamic batching that happens during the inference. This is because of mixing the prompt and token generation phases together. Next. By using our transformer kernel optimization and adapting the deep fusion to different byte sizes, here we are showing the latency improvement compared to a very good baseline that we see up to 20% latency cost reduction for the different byte sizes or token length here. Next. So as the next part of the composition of the optimization that we have in the inference system, we have the many GPU dense optimizations for multi-node, multi-GPU systems. So as these transformer models gets larger, we need to scale across the nodes, but tensor slicing is not the best solution. Is not only the best solution because we will have very large communication overhead if we use tensor slicing between nodes. So pipeline parallelism can help us here, but it's normally implemented for training, and this is not as efficient for the inference. So to get the best efficiency here, we have 2 challenges. First, the data dependency between the token generation phases and the load imbalance issue between prompt and token generation phases. And also we have the memory and communication overhead because during the inference, we are caching the results, and also the data that we are communicating between the GPUs has dynamic tensor shapes, which results in serialization and deserialization issue. So to answer these challenges, we implemented the inference optimized pipeline parallelism for DeepSpeed inference that has efficient pipeline schedule to handle the token dependency and hybrid schedule for addressing the load imbalance issue and the memory and communication optimization. Next. So regarding the pipeline schedule, so here we are showing the schedule of a pipeline during the training for the that is using the training schedule for the inference during the token generation. So as we see, there is a large bubble between a batch with the second token generation phase, and to remove these bubbles next. We actually don't have any dependency between the token generation of a batch with the next batch. So we can just modify the schedule so that they issue the next token much earlier. And next, the pipeline is very imbalanced between the prompt and token generation phase. On the right figure here, we see that the prompt part has many number of tokens, and it results in a long bubble in the system. So to resolve that issue, we can reduce the prompt length and divide it into smaller micro batches. But then we have the problem of increasing the token generation phase. And that's because the token generation phase is normally memory bound. So here, let's consider an example of a micro batch size of 8, taking Y latency. If we reduce the batch size to 4, we only double the latency, and this is because of reading the model parameters twice. So to resolve that issue, we come up with a hybrid schedule that has smaller byte size during the prompt part, and for the token generation, we fuse the batches together in order to get better throughput on the token generation, and also remove the bubbles during the prompt part. So regarding the memory and communication optimization, the issue that we see is that by running the large batch inference, we need a high memory usage, and this is because of saving the key and value during the inference for all the infrared requests. And to handle that issue, we use the CPU memory to offload a part of the KV cache. And for this, we have a double buffer memory that we write the current data while prefetching the next. And we also have this upload policy that we upload until the part that we can saturate the PCIe bandwidth. And by this, we can increase the byte size by about 30% and resulting in 25% speed up. For the communication optimization, we have a customized way of communication that we use a metadata that show the amount of data that we want to transfer ahead of time, so that we can remove the serialization, deserialization issue. And also it eliminates the CPU to GPU traffic that was seen in the previous approaches. So here, next, we show the improvement of each of these techniques. First, by the pipeline schedule, we can get up to 2x improvement. Next, by using the memory offload, we add another 25% improvement. With communication optimization, we have another X of improvement. And by using our transformer kernel, we can get up to 4.3x better throughput for this 530B inference system. So the last piece of this optimization that we have is for the sparse architectures. So we can use all the techniques mentioned in the previous slides for the dense part, and for the sparse part, we have different way of parallelism. And since this sparse architecture has both the dense part and also the sparse part, we can build a symphony of parallelism to optimize these kernels. And also, we have the optimized kernel to handle the sparsity, and we also use a parallelism coordinated optimization. So here we show the MOE system inference. As we can see, we can get better performance up to 7x improvement for trillion scale models. And as you see on the left figure, we can run a trillion parameter model size at 25 milliseconds, which is running inference at unprecedented scale and speed. Next. So having all these optimization for many GPU systems, now we come to the zero inference that enables democratizing massive model inference for data scientists who doesn't have access to many GPUs. So for running inference on single GPU devices, we use all different types of memory available, such as GPU, CPU, and NVMe to fit massive models. And this technique has been built on top of zero infinity and has been optimized for the inference. So the first key result that we want to show here is that with the same system architecture compared to a baseline PyTorch, we can run 4x larger model size. And second, next, regarding the efficiency, we can get up to more than 50% of the hardware peak throughput by using the zero inference, and also we can run much larger models. So with this, I pass to Joey to talk about compression.
Yeah, thank you, Reza. So hi, this is Joey. Next, I will talk about another interesting line of work we have been doing, which is compression. So compression includes two parts. One is compress the training and the other is compressed for inference. The overall objective here is to improve the efficiency of DNN training and inference with compression algorithm to deliver speed, boost model quality, and reduce the cost. On the training side, we have developed novel compression techniques that modify the training algorithm to improve the training efficiency. To give a few examples here, we implemented the sparse attention kernels. This is a technique that explores the intrinsic sparsity exists in the self-attention layer of transformer model that allows for the users to train MLP models with 10x longer sequence length, but with the same training cost. We also introduced progressive layer dropping, which explores the coarse-grained sparsity in the layer updates. As you can see, DNN train is in an iterative and expensive process. However, do we really need to update every single layer in every mini batch iteration? The answer is no. By skipping some of the layers and the sparsely update the model in every iteration, we can achieve up to 2.5x faster training speed while getting similar accuracy on downstream tasks. Finally, we also develop a family of compression techniques called one-bit compression that tackles expensive communication overhead introduced in large-scale model training on massive GPUs. Our most recent work, 1.0 ADAM, reduces the communication volume by 26x, while leading to 7 times faster end-to-end training time for both popular transformer models and the computer vision models. On the inference side, the need of compression is even more pressing to reduce latency and cost. However, existing methods have their challenges. It is hard to systematically compose different compression techniques for the best outcome. There also lacks efficient inference system to execute compressed models. To address those challenges, we have been actively working on building a library called DeepSpeed compression. The input of the model is a trained model with some latency, accuracy, and model sizes. And the output of the library is a compressed model that delivers fast speed, smaller model size with dramatically shortened compression time. Inside the library, we have two main components to address the challenges we talked about. The compression composer that automatically handles the complexity of composing different compression techniques to get highly compressed model checkpoints. The inference engine generates highly efficient code for the compressed model to minimize the latency. That's what Reza talked about, like, for example, those few the int8 kernels. Building the whole library is a significant effort, and at this stage, we have been focused on implementing the compression composer on the training side, such that it can compose techniques such as efficient architecture, distillation, and quantization, as well as some other inference engine support that are critical for our users. Along the way, we have been developing novel technologies that achieve the state-of-the-art results. Our extreme compression technique reduces the model size by 50x, and next, I will focus on the other two techniques. One is the zero quant, another is the PRMOE. So for zero quant, it's a cost-free integer quantization method. Before going into details, let's take a look at the current most popular quantization method, which is quantization-aware training. The full pipeline looks like this. You have a FP16 or FP32 model. You have to collect the training data and the GPU resources. After that, you do a trial and error loop in order to find the best hyperparameters for quantization. At the end of the loop, you get the quantized model. However, we know that for nowadays, due to the private and confidential issues, sometimes the training data is unavailable. Also, a large number of GPUs are usually required to train the model, particularly for those large transformers. To make things worse, hyperparameter tuning is generally very time-consuming. To address those issues, here we present our zero quant technique, which doesn't need any data or GPU for compression. As such, it doesn't have any training cost since it's a data-free and a GPU-free method. You may wonder, how can we achieve this? There are two very important techniques we use here. One is the fine-grained quantization scheme, another is the DeepSpeed specialized int8 inference kernels. So for fine-grained quantization, we mean here like instead of quantizing a FP16 weight matrix from FP16 to int8 with a single scaling factor, we quantize it with like different groups. As such, you will have like different quantization scaling factor for different groups, and you can significantly reduce the quantization error. To verify the performance, we applied quantization-aware training and zero quant on GPT-3 style model with 125 million parameters. As can be seen, compared to quantization-aware training, zero quant doesn't require any GPUs and time, and it's data-free. And more importantly, zero quant achieves better accuracy and better wiki text perplexity. Besides this smaller model, we also applied zero quant on one of the largest open source model, GPT-NeoX, which has 20 billion parameters. Due to the huge cost of QAT, here we just give an estimation instead of really performing QAT. So the estimation for QAT for this large scale model is that you roughly need 256 GPUs for 20 days, which generally not affordable by most of the researchers and the practitioners. However, apply zero quant, you don't need all those resources, and you can reduce the GPU latency from 2 times 65 milliseconds to 1 time 25 milliseconds. So this 2 means that you need 2 GPUs. And the entire reduction is 5.2x. Besides this, the accuracy degradation of zero quant is within 0.1%, which is negligible for most of applications. So besides applied quantization, we also design our new architectures. Reza and Panj already showed a great opportunity for DeepSpeed to do the inference and training. And one of the current most popular model architecture is MOE. However, the main challenge of MOE is that it has 8x more parameters than the quality equivalent dense model. As such, for training, it requires like a larger memory footprint. You need to, like, for example, increase your training GPU by 8x. And also it means like slower inference because you need to load these parameters. Reza already showed that the parameter loading is the main bottleneck for inference. So in order to resolve this issue, here we propose a new architecture called PRMOE, which is a parameter efficient MOE. So first of all, the standard MOE architecture, it uses a homogeneous layer structure. Basically means for every layer, you have the same layer structure. Like you have the same number of experts and each expert has the same architecture. And in order to reduce the number of experts, we design a new architecture called a pyramid MOE, which uses more experts in the last 2 layers and reduce the number of experts in the previous, like layer 1 to layer L-2. The designs actually come from the inspiration of convolutional neural networks. As we know, for convolutional neural networks, we usually use more channels for the last few layers and use like fewer channels in the first like few layers. Another thing we want to address is that most of MOE architecture is a plain like structure, which basically means every layer is an MOE layer, and you will need to choose different experts to process each of the token. Or sometimes people use top 2 MOEs. So basically you choose 2 experts to process like each token. However, this top 2 MOE will use extra communication cost. To resolve this, we introduce our architecture called the residual MOE. So instead of choosing like single expert or like 2 experts, we use a fixed MLP plus an expert to address the communication issue and the plain structure issue. So the benefit of our residual MOE is that you don't have like extra communication cost, and this expert can be used to correct the repetition of the MLP part. Combine the pyramid and residual MOE together, we have our design PI MOE architecture, which can significantly reduce the compute and the communication cost of the original MOE architecture. And beyond that, we also have our MOE specific knowledge distillation method. We call it MOS, which is the first MOE to MOE knowledge distillation work. By combining PIMOE and MOS together, we can reduce the MOE architecture's parameter by 1.9x to 3.7x, while achieving similar accuracy as the original baseline. So here are the 4 lists of the papers we discussed today. If you are interested in reading more about the topics DeepSpeed is covering like in the past 2 years, you can also read our blogs. So thank you all. That ends the talk.